Modules and Homological Algebra, Lecture 6, Problem Session. We start with the following problem. Prove that the free monoid on 2 letters is not isomorphic to the free monoid on 3 letters. Solution. Let us show even more, namely, that there is no surjective homomorphism from the free monoid on 2 letters A and B to the free monoid on 3 letters X, Y, and Z. So in order to prove that there are no such homomorphisms, let phi be a homomorphism from the free monoid on A and B to the free monoid on X, Y, Z. Denote by U the image of A under phi and by W the image of B under phi. And note that, more or less by definition, the letters A and B generate the free monoid on these 2 letters. So any non-identity element of this monoid is a product of A's and B's in some order. Therefore, we will consider several cases. Case 1 is when both U and W are the identity. Then any product of identities is the identity, so the image of the whole free monoid on A and B under phi consists of the identity. And then phi is, of course, not surjective. Case 2 considers the case where U is the identity, but W is not the identity, or vice versa. So this is the same, of course. So let us assume that the word W, which is not the identity, has length k. So k is a positive integer. Then the image of the whole free monoid on A and B consists of the products of U, which is the identity, and W. So it consists of the identity W, WW, WWW, and so on. Only powers of the word W. And then, of course, the length of the identity is 0, the length of W is k, the length of WW is 2k, and so on. So this image contains at most one element of length 1. So this homomorphism cannot be surjective because the free monoid on 3 letters has 3 elements of length 1, the letters. And finally, consider the situation when both U and W are not equal to the identity. Then the image of the free monoid on A and B consists of the following words. So we have the identity, of course, we have U, we have W's, and we have UU, UW, WU, WW, and so on. So on all words in the alphabet U and W. And this image contains at most 2 elements of length 1, so these are U and W. They might be of length 1 or might be of greater length, but it is for sure that all other words, UU, UW, and so on, these have length strictly greater than 1. And again, the free monoid on 3 letters has 3 words of length 1, and here in the image we have at most 2. Therefore, this homomorphism cannot be surjective. This completes problem 1. Problem 2. Consider the free monoid F on 2 letters A and B. Prove that the submonoid of this monoid, generated by the words A squared, B squared, and AB, is isomorphic to the free monoid on 3 letters X, Y, and Z. Solution. Denote by M the submonoid of the free monoid on A and B, which is generated by the words A squared, B squared, and AB. By the free property of the free monoid on X, Y, and Z, there is a unique surjective homomorphism phi from this free monoid on X, Y, and Z onto M, which sends X to A squared, Y to B squared, and Z to AB. This is exactly the free property of this monoid. So it is enough to show that phi is injective. So this homomorphism is by construction surjective. If we show that it is injective, it's an isomorphism, which proves the assertion of our problem. So assume that some element W in the free monoid on A and B belongs to the image of phi. Let us show that the preimage of W can be uniquely determined. So which means that each element has unique preimage, so the homomorphism is injective. Let us proceed by induction on the length of W. So if the length of W is 0, it's the identity element, and so the only preimage is obviously the identity element. So assume that the length of W is greater than 0, then it's greater than or equal to 2. Let us now write W as P, Q, U, where P and Q are letters, and consider three cases. If PQ is equal to AA, then any element in the preimage of W equals X followed by a preimage of U. This is because X goes to AA, so only the letter X goes to AA, since phi is a homomorphism. Similarly, if PQ is BB, then any element in the preimage of W equals Y, because it's only Y which goes to BB, followed by a preimage of U, since phi is a homomorphism. And if PQ is equal to AB, then any element in the preimage of W equals Z, because it's only Z which goes to AB, followed by a preimage of U, since phi is a homomorphism. And U has strictly smaller lengths, so its preimage is uniquely determined by induction, and the proof is complete. Problem 3. Consider the symmetric group S3 on 1, 2, 3. Prove that the permutations X, so this is a transposition of 1 and 2, and T, which is a transposition of 3 and 2, generate the symmetric group S3, and that the following set is a set of defining relations for these generators. So the set of defining relations is the following set of relations: S squared is equal to E, T squared is equal to E, and STS is equal to TST. Solution. Let us recall that the symmetric group S3 consists of the following 6 elements. So all permutations on 1, 2, and 3. So we can send 1 to 3 respectively to 1 to 3, this is the identity, 2, 1, 3, this is S, 1, 3, 2, this is T, and then we can also have 3 to 1, 2, 3, 1, and 3, 1, 2. And then we can readily determine that, of course, the identity element is the permutation 1 to 3, the element S is 2, 1, 3, and the element T is 1, 3, 2. And then the permutation 3 to 1 is exactly STS. So let's check. If we do S, we go from 1 to 2, then T goes from 2 to 3, and then S goes from 3 to 3. So 1 goes to 3. Similarly, 2 goes to 1, to 1, to 2. So 2 goes to 2, and then 3 only can go to 1. So this element is equal to STS. Next, the permutation 2, 3, 1 is equal to ST. Indeed, if we do T, 1 goes to 1, and S1 goes to 2, so 1 goes to 2. 2 goes to 3, 3 to 3, so 2 goes to 3, and then 3 can go only to 1. And similarly, TS is the permutation 3, 1, 2. This means that any permutation is a product of S's and T's, of course, every non-identity permutation, and this means that S and T generate S3. Now we have to check that our set of defining relations is a full set of defining relations. It is very easy to check directly from the definitions using direct computation that S squared is equal to T squared is equal to the identity, and that STS is equal to TST. So our S and T satisfy these relations. So let us denote by G the group which is given by our presentation. It has two generators S and T, and the relations S squared is equal to T squared is equal to the identity, and STS is equal to TST. By factorization lemma, we have a surjective homomorphism from the group G to S3, which sends S to S and T to T. It remains to prove that this homomorphism is injective. And in order to prove this, we simply need to show that the group G consists of at most 6 elements, and that will be it. By construction of the free group, any element of the group G can be written as a word in the generators S and T and their inverses S inverse and T inverse. But our first set of relations says that X squared is equal to the identity and T squared is equal to the identity. which means that S is equal to S inverse and T is equal to T inverse. So this means that any element of G can be written as a word just in S's and T's. Moreover, since S square and T square is the identity, it is enough to consider the words where S and T alternate. So the words of the form S, T, S, T, S, and so on, or T, S, T, S, T, S, and so on. Of course, we have the first 6 words, the identity S, T, ST, TS, and then STS. And we know that by our last relation that STS is equal to TST. And we claim that any other word is equivalent to one of these. And we prove this by induction on the lengths of the word. So assume that we have some word of lengths greater than 3, which starts with ST, ST, and then something. The first 3 letters STS, using the last relation, can be rewritten as TST. So this word is equal to TS, TT, W. And now we have T squared in the middle, which is the identity, so we can contract it and get the word TSW, which has strictly smaller lengths. So this proves by induction that any longer word can be reduced to one of these 6 words, and similarly for the words starting with T. And this completes the solution to problem 3. Problem 4. Show that there is a unique group homomorphism from S3 to the group of all invertible 3 times 3 matrices with complex coefficients, which sends our transposition S, which transposes 1 and 2, to the matrix 1, 1, 0, 0, minus 1, 0, 0, 0, minus 1, and the transposition T, which transposes 2 and 3, to the matrix minus 1, 0, 0, 1, 1, 0, 0, 0, minus 1. Solution. It is obvious that both matrices are not degenerate because their determinant is just the product of diagonal elements, which is non-zero. So at least on S and T, the images of S and T under this homomorphism to B are non-degenerate matrices, so that's good. And in order to establish that we can uniquely lift it to a homomorphism from S3 to the group of invertible 3 times 3 matrices, we simply need to check that the images of the generators satisfy the defining relations which we established in the previous problem. This is exactly the point of the factorization lemma. So we need to check that these 2 matrices satisfy the defining relations S squared is equal to T squared is equal to the identity, and STS is equal to TST. And this we can check by direct computation. So for the first relation, let's see if we take the matrix 1, 1, 0, 0, minus 1, 0, 0, 0, minus 1 and square it. So we should take 1, 1, 0 and multiply with each column. We get 1, 0, 0. Then 0 minus 1, 0 multiplied with each column gives us 0, 1, 0. And 0, 0, minus 1 with each column gives us 0, 0, 1. So we get the identity matrix. And similarly for T. In order to check the relation STS is equal to TST, we just take the product of these matrices, and we claim that the product STS is equal to the matrix 0, minus 1, 0, minus 1, 0, 0, 0, 0, minus 1. Indeed, let's take the first basis vector 1, 0, 0, and look where it goes under this product. So here we take this matrix, we get 1, 0, 0. Multiply with this, we get minus 1, 1, 0, and here we will get 0, minus 1, 0. That is exactly the first column here. So for the second basis vector, we have 1, minus 1, 0, multiplied here gives us minus 1, 0, 0, minus 1, 0, 0. That's exactly the second column. And for the third basis vector, we get 0, 0, minus 1, 0, 0, 1, 0, 0, minus 1. That's exactly the third column. So this checks that STS is this matrix, and exactly in the same way, TST is also equal to this matrix. So STS is equal to TST. And this completes problem 4. Problem 5. Determine some presentation of the additive group of integers with respect to the generating set consisting of 2 integers, 2 and 3. Solution. So we have two generators. We have to consider the free group on two letters, A and B. By the free property of this free group, there is a unique homomorphism phi from this free group to the additive group of integers, which sends A to 2 and B to 3. And then we can easily guess some relations. It's clear that, first of all, addition is commutative, so 2 plus 3 is equal to 3 plus 2. And it's also clear that 2 plus 2 plus 2 is equal to 3 plus 3. So these relations are obvious. So we claim that the corresponding set of relations in our free group is the full set of defining relations. For this, let G be the quotient of our free group on A and B by the normal subgroup generated by the relations AB is equal to BA. This corresponds to 2 plus 3 is equal to 3 plus 2. And AAA is equal to BB. So this corresponds to 2 plus 2 plus 2 is equal to 3 plus 3. So by factorization lemma, just as in one of the previous problems, the map phi factors through G. So what we want to prove? We want to prove that G is isomorphic to Z. So this factorization is actually an isomorphism. So for this, let us now estimate how many elements the group G has. So every element in G is a word in A inverse, B, and B inverse. That's from the definition. But A and B commute. So multiplying with A inverse on both sides, we have that B and A inverse commute, and A and B inverse commute, and the inverses of A and B commute. And so in any such word, we can commute all A's and A inverses to the left, all B's and B inverses to the right, cancel what we can between A and A inverse, and cancel what we can between B and B inverse. So the outcome will be a word of the form A to the power I, B to the power j, where I and j are integers. Next, we use the relations that A cubed is equal to B squared. So using this relation, we can reduce I modulo 3, because any I cubed can be rewritten as B in some power. And so we may assume that I belongs to 0, 1, or 2. So we pick some representatives of integers modulo 3. And then it remains to know that each integer can be uniquely written in the form 2 times I plus 3 times j, where I is 0, 1, or 2, and j is an integer. And this means exactly that our map phi from G, so the factorization from the map phi from G to the integers is bijective. And this completes problem 5. Problem 6. Show that there is a unique group homomorphism from the group of integers to the group of invertible 3 times 3 matrices, which sends 2 to the matrix 3 to 1, 2 to 0, 1, 0, 3, which sends 3 to the matrix 6, 4, 4, 4, 2, 4, 4, 4, minus 2. Solution. Let's start by checking that actually these two matrices are non-degenerate, so the formulation of the problem is well defined. For this, we need to compute the determinants. The determinant of the first matrix is the following expression. So we have 3 times 2 times 3, plus 2 times 0 times 1, plus 2 times 0 times 1, minus 1 times 2 times 1, minus 2 times 2 times 3, minus 0 times 0 times 3. And this can be computed as 4, which is non-zero. So the first matrix is non-degenerate. Similarly, the determinant of the second matrix is the following expression. So the diagonal gives us 6 times 2 times minus 2, plus 4 times 4 times 4 twice, minus 4 times 2 times 4, minus 4 times 4 times minus 2, minus 6 times 4 times 4. And this is equal to 8, which is again non-zero. So this matrix is also non-degenerate. In the previous problem, we found out that 2 and 3, they are generators of the additive group of integers, and the set of defining relations for these generators consists of two relations, AB is equal to BA, and A cubed is equal to B squared. So in order to prove the assertion of our problem, we need to check that our matrices satisfy these defining relations. So first, for the relation AB is equal to BA, we compute the matrix for A times the matrix for B, and we get the matrix 30, 20, 18, 20, 12, 16, 18, 16, minus 2. So let's check, for example, 3 to 1 times 6, 4, 4. 18 plus 8 plus 4. This is exactly 30. Or 2 to 0 times 4 to 4. 8 plus 4 plus 0. This is exactly 12, and so on. Similarly, if you multiply these matrices in the opposite order, we will get the same matrix. Let's check some elements. Let's say first row times third column. 6 plus 0 plus 12. This is 18. Or third row times second column. 8 plus 8 plus 0. That's 16. So we see that AB is equal to BA, and this is this common matrix. Next, let us check the relation A cubed is equal to B squared. So we have to compute the cube of the first matrix. So if we square this matrix, we get 14, 10, 6, 10, 8, 2, 6, 2, 10. So indeed, 3 times 3 plus 2 times 2 plus 1 times 1, it's 14. 3 times 2 plus 2 times 2 plus 0, so it's 6 plus 4, 10, and so on. And now if we multiply this matrix with the original matrix again, we get 68, 48, 32, 48, 36, 16, 32, 16, 36. And similarly now we have to compute the right-hand side, so the square of the second matrix, and we claim that it is equal to the same matrix, 68, 48, and so on. So let's check at least some elements. 6, 4, 4 times 4, 2, 4. 6 times 4 is 24. 4 times 2 is 8. It's 32. 4 times 4 is 16. It's 48. And so on. We can check. So we get that A cubed is equal to B squared. So all relations are satisfied. And this means that there is a unique homomorphism from the additive group of integers, which sends 2 to this matrix and 3 to this matrix. Problem 7. Determine some presentation of the algebra of all upper triangular 2 times 2 complex matrices. Solution. So the algebra of all upper triangular 2 times 2 complex matrices is the algebra which consists of all matrices of the form x, y, 0, z, where x, y, and z are complex numbers. This is a three-dimensional algebra. It's generated obviously by any basis of this algebra, so let's take the following basis of this algebra. The matrix A is 1, 0, 0, 0, the matrix B is 0, 1, 0, 0, and the matrix C is 0, 0, 0, 1. In this basis, we can compute the multiplication table. So A squared is A, AB is equal to B, AC is equal to 0, BA is 0, B squared is 0, BC is B, and then CA is 0, CB is 0, and C squared is C. So that's a complete multiplication table in this basis. Our claim is that the algebra A is given by the following presentation. So we take our bases A, B, and C as the generators, and we take our multiplication table as relations. So A squared is equal to A, AB is B, BC is B, C squared is C, and all other products are 0. So that's our claim. Let's prove it. Let us denote by B the algebra which is given by this presentation. By factorization lab, we have a surjective homomorphism from B to A, which extends the identity map on our basis A, B, C. So to prove our claim, we just need to show that the dimension of B is at most 3. By definition, the elements of B are linear combinations of words in the elements A, B, and C. And our relations say if you have any word which has lengths greater than 1, we can take any two letters in this word and multiply them, and using our relations, we can reduce the length of this word. Therefore, any element of B can be written as a linear combinations of words in ABC which have lengths at most 1. But also from the relations, we see that A plus C is equal to the identity. So if we take A plus C and multiply with anything, we get that element back. So A plus C times A is A. A plus C times B is B. A plus C times C is C. So we also have the additional relation from our multiplication table that A plus C is equal to the identity. And that's the only word of length 0. So if we take it away, we get that any element of B is a linear combination of letters A, B, and C. And so its dimension is at most 3, which means that this homomorphism must be injective, and so bijective. This completes the proof. And the last problem 8. Show that the algebra of all upper triangular 2 times 2 complex matrices does not have any singleton generating set. Solution: let A be the algebra of all upper triangular 2 times 2 complex matrices. Assume that A has a singleton generating set consisting of an element U. Then, by the definition of the generating set, A is a quotient of the free algebra on one element. And we know that the free algebra on one element is the polynomial algebra in this element. And any polynomial algebra is commutative. So our algebra A, being the quotient of a commutative algebra, should be commutative. But the algebra of 2 times 2 upper triangular matrices is not commutative. As we can see from this multiplication table, it's not symmetric. And this means that we have a contradiction. So our assumption that A has a singleton generating set is false. Let us finish with some problems and questions. Question 1. Prove that the free group on 2 letters is not isomorphic to the free group on 3 letters. Question 2. Prove that the subgroup of the free group on 2 letters generated by the 3 words a squared, b squared, and ab is isomorphic to the free group on 3 letters. Question 3. Find some presentation for the symmetric group S4 on the elements 1, 2, 3, and 4. Question 4. Show that there is a unique group homomorphism from S4 to the group of non-degenerate 2 times 2 complex matrices, which sends a transposition of 1 and 2 to the matrix 1, 0, minus 1, minus 1, the transposition of 2 and 3 to the matrix 0, 1, 1, 0, and the transposition 3, 4 to the matrix 1, 0, minus 1, minus 1. And question 5. Find some presentation for the algebra of upper triangular 2 times 2 complex matrices, which has 2 generators. Thank you very much, and see you next time.